Okay, is that all good? You guys can see the first slide.
Yes.
Okay, thank you very much. Okay, so I realized that I don't have a camera. Usually when I present on Zoom, I'm using my phone, but I had to present on my desktop today. So I've put an image of myself. I'm on the right. My name is Mara Lorenka, as Bismarck had just mentioned, and on the left or on my right here is Professor Chris Curtis. He's from the University of Johannesburg, but when we did the study, he was still at University of the Witwatersrand. And so this project was part of my master's project, and we've subsequently written a journal article that's been submitted to Water SA. It was accepted for publication, subject to review. So those revisions have been done, and now we are just waiting to hear back from Water SA on the publication. And so we'll just get going. So the title was The Influence of the Eastern Basin Acid Mine Drainage Chemical Treatment Plants on Water Quality along the Blesbokspruit Wetland in South Africa. So this Eastern Basin AMD treatment plant is a new treatment plant. It was commissioned in August 2016, and so there's hardly any academic literature regarding this. Most of our sources are based on media reports, and so this would be one of, probably, well, to my knowledge, the first paper that deals with this new treatment plant that is upstream of the Blesbokspruit Wetland. Okay, so just some background, and as I'm sure most of you know about the issues surrounding acid mine drainage, and it being one of the most destructive forms of pollution on water quality. So during mining operations, water is pumped out, obviously for mining operations to occur, and once those mines close, those mine voids fill up with water, and we have the process of acid mine drainage, where the pyrite mixes with water and oxygen, and it forms ferric hydroxide and sulfuric acid. And this AMD pollution eventually decants, just meaning it just pours out onto the surface, and it's very destructive to the natural environment. On the right here is an image from a field trip that we took in February of 2017 as part of my honors, one of my honors courses. And this is at the Blesbokspruit. This is where the AMD is decanting there. This is in the Western Basin. So continuing from there, as I'm sure we're all aware of the Wit gold mining, we've got three main basins. Over here, there's actually Forward, West Rand, West Line, Central Rand Basin, and East Rand Basin. And so we can see that mining and acid mine drainage is a very broad geographical problem. And what we are focusing on, or what the study focuses on, is in the East Rand Basin, in the small mining town of Springs. And the Blesbokspruit basically flows through this area, and where it terminates, it's around about here in Nigel. So we're focusing on the East Rand Basin, primarily around Springs. Okay. All right, so just some historical context. The mine that we're focusing on here is the Grootvlei proprietary mine. It was in operation from 1934 until 2010. And it's located within the Blesbokspruit Wetland. I will show a site map just to indicate the position of the mine in comparison to the wetland. So it's upstream of the Vaal Bird Sanctuary, which lies in the southern half of the wetland itself. And the Blesbokspruit Wetland was first accepted as a Ramsar Wetland of international importance in 1986. So on the top left image, this is an image of AMD as an active mine in the Western Basin. On the right image, this is an image that Professor Chris Curtis and I, when we saw this bird, he took the image. one of our field trips to Vaal, this is a squawker heron. And on the bottom left, this is a black egret. Both of these birds were photographed in the Vaal Bird Sanctuary. And so we're moving on, just with regards to the historical context of the mine. Grootvlei started major pumping in 1995, but the resultant precipitation of red AMD sludge at the surface meant that it was ordered to stop, and it was ordered to stop by national government. And in 1996, the wetland was actually placed on the Montreux record in response to the contamination of this AMD, red AMD sludge that was precipitated out onto the surface. And actually, the wetland still remains on this register. So the Montreux record is basically a register that lists potential or endangered Ramsar sites. So Ramsar sites that no longer meet the Ramsar Convention standards. And so leading to, in 2020, I've looked it up, and the Blesbokspruit Wetland remains on this register. So it's still considered as degraded or with potential risks to biodiversity. Okay, so after being placed on the Montreux record, mining promptly began on condition that they treated underground water through the use of an HDS process, or a high density sludge process. So the high density sludge process is used throughout the world. We'll get into that. It's an active chemical treatment designed to neutralize acid mined water and allow for the precipitation and removal of heavy metals. So basically, the AMD water that is pumped up is treated with limestone or dolomite, and that raises its pH. And from there, the heavy metals that were once dissolved in the water can precipitate out, and those heavy metals are removed. So the original small HDS plant that was at the mine during operation, it did improve effluent quality. However, knowing basic chemistry, when we mix an acid and a base, we get salt and water, and so it produced water with a high dissolved salt content that was discharged downstream. Right, so after closure of the mine in 2010, recharge of previously dewatered areas would ultimately lead to decant. And so the TCCA, or the Trans-Caledon Tunnel Authority, was instructed to manage AMD within the three Basin. And the Eastern Basin AMD project is aimed at the short-term or phase 1 prevention to stop environmental critical levels being breached. And so the environmental critical level is the level in the mine void at the critical location which needs to be maintained and not allowed to rise in order to prevent decant of AMD and protect the environment. And this also includes groundwater resources. Okay. So moving on, as part of the TCCA phase 1, the Eastern Basin AMD treatment plant was commissioned in August of 2016. Okay, the plant, according to the press release, cost R1 billion to produce. It has the capacity to pump 108 million liters of water per day to mitigate against the pollution of underground water resources. So it's a very, very big plant. It's one of the largest HDS plants in the world. So the original HDS plant that worked during mining operations, now this is the new one. It's the same technology on a bigger scale. So if I just take you through the images here, there's three heavy-duty pumps that are pumping AMD water to the surface. They're pumping water from mine shaft number 3, and that mine shaft has got a depth of 1 kilometer, but they're pumping water from 150 meters depth of AMD water. From that pumping, the water is then mixed with lime, and it's neutralized. And so what we have is the formation of the sludge, is what we call the sludge, this brown liquid. And so if we have this kind of brown, heavy metal-rich liquid that is formed after the first neutralization. After some treatment, that sludge is removed. So the heavy metal sludge is removed through settling ponds and other gypsum crystallization and other processes. And that heavy metal sludge is then re-injected back underground to a depth of 700 meters below the surface. And so after the sludge is removed, the cleaner overflow of water that is formed from these settling ponds is then discharged into the Blesbokspruit. Okay, so that's the flow kind of diagram of the processes used within the by the treatment plant. And so we've got a few treatments. The first one is oxidation by aeration. This is basically the chemical reaction that we get when our pyrite and oxygen, our pyrite that comes from underground mixes with oxygen and water produces iron hydroxide and sulfuric acid. So it's the reaction that would occur anytime AMD was to decant onto the surface. And so the main treatment is a pre-neutralization with limestone or dolomite, and then a final neutralization with black lime and gypsum. And so the byproducts include iron hydroxide, gypsum, and magnesium sulphate. Here is an image of the lime thickener tank, and the new, so at the new AMD treatment plant in Eastern Basin, and the wetland can be seen in the background of this plant. And this photo was taken by Professor Curtis in 2017. Okay, so I just want to spend some time on this site map just to explain our methodology with regards to testing the impact of the new water treatment plant on water quality or surface water quality. Okay, so there is a large network of rainwater monitoring sites that are available for free access on the reservoir website. And 5 of these sites are within the Blesbokspruit Wetland. These sites have specific codes, sites B5, B16, B15, B17, B11. And the water quality for these sites from rainwater goes back to as early as 2008 with quarterly water quality reports published every quarter in the year. And so it provided an opportunity to do a BACI design, which stands for before-after control impact. So according to the site map, the river flows from north to south, if you just follow my cursor. So in a sense, site 1 has no real, the water treatment plant will have no real influence on site 1, and so it's named the control site. Site 2 is downstream of the water treatment plant, the first site that's immediately downstream, and so we've named that the impact site. And because we have this historical record of data from rainwater back since 2008, we can also compare a before and after. And so I'm going to get into the BAC design shortly. Sites 3, 4, and 5 mainly flow, we can call that the start of the Vaal Bird Sanctuary, although the wetland does start up at site 1. So sites 3, 4, and 5, we are just trying to see if this influence of the water treatment plant carries on further downstream at site 3, site 4, and site 5. And those are within the Blesbokspruit. And those 3 specifically are within Vaal Bird Sanctuary. Okay, all right. So the next slide. Okay, so the BACI design and hypothesis. So this is briefly what I was explaining earlier. We have a before situation and an after situation. So if we just start with the BA, the before situation, we are comparing site 1, which we've named the control site, to site 2, which is the site that's downstream of the AMD water treatment plant. But the conditions before, meaning that there's no AMD treatment plant at that time. So what we expect is that the sites should be similar. So that is our before versus after. And then afterwards, we would expect that site 1 and site 2 will be different because of the influence of the AMD water treatment plant. Okay, so through this design, we tested two hypotheses. Hypothesis 1 tests temporal change, so tests before versus after. So the hypothesis saying commissioning of the new HDS AMD water treatment plant in August 2016 has a measurable or statistically significant impact on water quality at the impact site, which is downstream of the water treatment plant, but not at the control site, which is upstream. Okay, so the first hypothesis testing temporal change, or the BA. Second hypothesis is testing the spatial difference, or the CI, the control and impact. So there is a measurable or statistically significant difference between control site and impact site, which 1 and 2 respectively, with the new treatment plant in operation. And that's for the time period after, because that's only when you can only do that comparison when the water treatment plant is in place. Okay. All right. So I just want to move on to the water quality guidelines used for this study. The water quality guidelines are the same water quality guidelines that are used in the water quality reports by the Blesbokspruit Forum, and those are for the Blesbokspruit catchment. They're also available from the reservoir website along with the rainwater data. And so in this catchment, they describe water as certain water quality variables as being either ideal, acceptable, tolerable, and unacceptable. And the colors are very important because these colors are translated in all the data tables and graphs that are shown from now until the end of the presentation. So if you see blue, it means it's doing well, it's ideal, it's what we want, or what the Blesbokspruit catchment is what is ideal for those specific water quality variables. Acceptable would be green, tolerable will be yellow, and unacceptable is not what is accepted for the Blesbokspruit catchment. Now, for this study, we only looked at water quality variables, which are shown here. There's 14 of them, and I will highlight the main ones that we're going to focus on with regards to the overall findings of the study. So moving on to test hypothesis 1. I know I need to try and avoid a lot of data tables, but I feel like this, if I go through this slowly, it would be quite easy to follow. So this is to test in temporal change. So here we've got two tests. The first test is to test whether our control site is actually that, if it is a control site. So we find that the differences in means between before the water treatment plant, so that's a 3-year period before, and the 3-year period after the water treatment plant. And so what we see, the only parameters that are different are aluminium and dissolved oxygen, where aluminium remained acceptable, although increasing by 121%. The values were still in the acceptable range. And dissolved oxygen at 3.06 milligrams per liter reduced to 1.92, but was remaining in the unacceptable category. All the other water quality parameters did not change in terms of, and actually all of them did not change in terms of the categories outlined by the Blesbokspruit Forum. And so we can say that our control site in terms of time is a good control site because there's not much changing in the form of water quality, especially with regards to the different categories that each water quality variable is placed in. The only notable one here is phosphate, and you can say that for the time period after after the water treatment plant came into commission, phosphate did increase, but we can attribute this to an upstream source because we know that the water treatment plant is downstream of this site. The second test is more significant, and so in the second test, we test sites at site 2 for the period before the water treatment plant started versus the period after. And we can see a different kind of situation where 8 of the 14 water quality variables have a significant difference, just meaning that if there's a difference that's statistically significant. And so we can see again, aluminium increased. Okay, this is what we saw also for control site 1. So that was maybe to be expected. The nutrients of ammonia decreased. Chloride increased. The main one that I want to highlight today is conductivity. Conductivity went from tolerable to unacceptable. So from 79 microsiemens per meter, now for the period after, on average, it was 130. The second one I would like to highlight is magnesium, going from 17 to 37, so from acceptable to tolerable. And the third one, and the most significant one, would be sulphate. Sulphate moved from ideal to unacceptable targets, and so did sodium, from ideal to unacceptable on average. Okay, so this is to test temporal change, and a very similar situation is seen when you're testing the spatial difference. So for test 3, we tested control site versus impact site, and so we only saw a significant difference in magnesium and phosphate, but those also remained very similar water quality targets. And actually, the difference between control site 1 and impact site before the water and treatment plant, there's very little difference between the water quality. So basically, the conditions before the water treatment plant, site 1 and site 2 were behaving very similarly. For test 4, it's a different story again. Here we test between control site and the impact site after the water treatment plant, and we can see that 10 out of the 14 water quality parameters have different, significant differences between them. And so it's a similar story where we see that conductivity goes from tolerable to unacceptable. Both sodium and sulphate go from ideal to unacceptable, to tolerable. And magnesium goes from acceptable to tolerable. So thank you for bearing with me with regard to those data tables. So what does this all mean? I think this image will be able to tell you exactly what our point we're trying to make here. So if we focus specifically on electrical conductivity, you can see that sites 1, 2, 3, and 4, and 5 are all outlined here with the specific either a dashed line in the color. And so we can see that for the period, 3-year period before the treatment plant started, from the start of 2013 to quarter 3 2016 or August 2016, all the sites behave very similarly. They all have a seasonal response that is quite similar. So from site 1 to site 5, we can say that water chemistry is very similar for all sites. We can say that maybe the downstream sites are slightly higher, but on just in general, when looking at this, we can see that they're all very similar. The situation after the treatment plant comes into or it gets commissioned is very, very different. Site 1, the dark black, so the black site, that this line here, stays quite similar to its previous behavior. So it was behaving very similar to what it was doing before, so it acts as a control site. But all the other sites have increased tremendously, which are all downstream of the water treatment plant. So just the big takeaway here, control sites mean before the water treatment plant was 71, mean after was 74, so it's acting as a control site. And the impact site, the mean before was 80 microsiemens per meter, and the mean after was 150. The same situation occurs here for sulphate. Oh yeah, sorry, I just forgot to mention that the colors actually represent the Blesbokspruit Forum water quality colors guidelines. So after the water treatment plant comes into play, conductivity now is reached unacceptable levels or at all sites downstream of the water treatment plant. And so the same can be said for sulphate, where the situation before is very similar water chemistry throughout all the sites with regards to sulphate, but after all the sites diverge from the control site. And so we've got control site mean of 103 before, 124 after. but the impact site has got 110 mean before and after almost 400. So we've moved from ideal to tolerable, and in some cases, at site 2, the red site, we've reached unacceptable levels. Okay, so the key messages, and if we include magnesium here, all three of them together, that all these sites before the treatment plant on the left here are behaving similarly, but when the treatment plant starts, we have a lot higher levels of conductivity, magnesium, and sulphate for all those downstream sites. And the reason why we included sites 3, 4, and 5 is to identify whether this chemical signature of in what we are calling an increased TDS, or total dissolved solids, would be carried out throughout the wetland. And we are seeing that exactly that. For example, conductivity is increased throughout the wetland from downstream of the water treatment plant. So it doesn't, so the wetland doesn't really take up a lot of the TDS. And the main thing is that both conductivity and sulphate have now reached unacceptable levels. Okay, so the Blesbokspruit waters had already been described as having a high TDS before the treatment plant came into operation. And that was during the time of mining when the original HTS plant was working. So it's reasonable to assume that phase 1 is beneficial in terms of treating heavy metals from underground AMD water and keeping the water below the environmental critical level. But the processes used by the plant is exacerbating salinity within the system. And of course, the conductivity and sulphate have reached unacceptable management targets, and they have a high potential to be damaging to the environment. So in an earlier study by Ambani and Annegarn in 2015, they found very similar results, but they found that water quality improved when the pumping stopped. And the current study shows that the new treatment plant has resulted in sulphate concentrations increasing sharply to a mean of almost 400 milligrams per liter in the downstream site, and that's levels that it's not seen since 2007, and that's when actually mining was occurring. So we would expect that after mining has stopped, that water quality would improve, but it's actually reaching levels that we had before when we were mining. And so, in fact, during the last years of pumping from an active mine, downstream sulphate levels were lower than they were during the last quarter of 2019 with the treatment plant in operation. Okay, so as I've mentioned, the Blesbokspruit was placed on the Montreux record in 1996. It's still on that record. And the increasing TDS has been described in other papers, and changed flow regimes have been linked to a decline in aquatic biodiversity and encroachment of invasive reef species. Just in terms of how TDS affects aquatic biodiversity, it's found to affect the individual aquatic species adaptations, community structure, and microbial and ecological processes. And the long-term impacts of the major increase in TDS are unknown, especially with regards to the biodiversity, and merits further study. So as far back as 2000, Pilsen et al. Reported that Grootvlei in the former Western Areas gold mine contributed as much as 26% of the salt load that entered into the Vaal Barrage from point discharges in 2000. So that was simply from mining. And we calculated some fluxes from the figures that come out of that paper. And so we calculated that 15.21 tons of magnesium per day and 271 tons of sulphate per day were coming out of those two mines, out of Grootvlei mine from water discharges alone. So not accounting for upstream concentration. So it's simply just from the mine. If you compare that to the last quarter of 2019, we have values of 6.44 tons per day of magnesium and 81.62 tons per day of sulphate. So it is a slight improvement from levels during 2000 when we had an active mine. But we attribute that to, obviously, we don't have mining occurring now. So perhaps those, that AMD water isn't as highly concentrated in those two parameters as it was before, and most probably due to lower flows under the current situation compared to when it was mining back in 2000. So I'd like to just show you some evidence of the increased salinity. These are images that I took on. I would go to Microbial once a month for a full year during my master's, and you can see that the salt crusts are formed on the surface. So especially during the dry season, when these areas will be inundated with water. During the dry season, it dries up, and obviously we have these salt crusts that have formed. And we did a simple transect from the river to an outer edge where we have a tailings dump. And if you can see, according to the conductivity results, the highest concentrations of soil conductivity are actually near the water's edge, and they get reduced quite dramatically towards where we have our tailings dumps. So these are numbered from 1 to 9. And so these, I just did them in this order so that you can see that the highest values are closer to the Blesbokspruit, and we cannot really attribute high soil conductivity to the tailings dump just based on this small exercise. If you look at soil pH, there's no real clear relationship between the pH of the soil and the proximity to the river. So another point that I wanted to highlight, that source from McCarthy 2011, he mentioned that the Vaal Dam is upstream to the Vaal Barrage. So this diagram is a little bit backwards because downstream goes from right to left. But the salinity more than doubles from Vaal Dam downstream in the Vaal Barrage. And so a lot of the time, when water is released from the Vaal Dam, it's released to dilute this water. But that water we need for drinking purposes, as we all know. And so that just is highlighted by that paper. So the issues of salinity have been there since 2000, and what we're saying is that Eastern Basin treatment plants may actually prove to exacerbate salinity within the Vaal. Currently, magnesium and sulphate levels are acceptable for livestock, which is takes place downstream of the Blesbokspruit, but farming takes place downstream of the Blesbokspruit, but conductivity levels need to be maintained below 40, and that's been exceeded. So people that need to irrigate their crops would have to treat that water. There were some improvements. So for example, iron, the nutrients of ammonium, phosphate, and nitrate were all reduced. But what we suggest from this reduction is that because there's a lot more water that's been inputted into the system through the HCS treatment, that water is coming from underground. So we're not expecting it to have high nitrate, ammonium, phosphate values, because we would expect that from, for example, sewage works, but that water is coming from underground. And so we have a lot more influx of water coming from underground that doesn't have nitrate, ammonium, phosphate in it. And so what we attribute this improvement to simply a dilution effect, where we have increased flows, where the concentrations are the same, but now, sorry, the amount of the parameter is the same, but the concentration is lower because of increased flows. Okay, so what can we do about this? The requirement for secondary treatment. So HCS system is highly effective. It's used throughout the world. And the increase in salinity and sulphate is expected with an HCS system simply because of the simple chemistry that happens. But some South African mines have already established additional secondary treatments. So we're talking about treatments to remove the salinity. That's already happened in the Western Areas gold mine, where they use the GYP-CIX process, which has got both high water and economic recovery. So they actually sell the metals that come out of this process and the salt. And at Optimum Mine in Mpumalanga, they use reverse osmosis to treat mine water and actually convert it to a potable water supply for communities in a water-stressed area. Okay. So in conclusion, the main findings of this paper is that the issues of salinity have yet to be tackled and have worsened under the current treatment, so especially with regards to conductivity and sulphate. And so what was planned in the long-term solution, or phase 2, to remove that salinity needs to be put in place as quickly as possible. And it's outlined in the South African National Water and Sanitation Master Plan. It states that treated AMD will need to make a significant contribution to South Africa's water mix by 2020. So AMD will be a part of South Africa, of Gauteng's at least, water supply, and we need to treat it to a better state. So, thank you very much for your patience. I know I went over time, and that's my presentation.